Hey all! So I've finally had time to work on my high vacuum project. I've wanted a high vacuum setup for a while since it opens up the doors for a lot of physics and material science projects. I've been collecting parts for like half a year and I finally made the first steps into building a central controller. That's what you see here. I want to centralize all my vacuum gauges and all my pump controls and stuff like that, so I have like a sturdy, beefy rack unit I can put in a 19-inch rack. So this is my turbo pump. This is my main vacuum pump. It's an Edwards EXT 255H. And the pump came with this nice little directly mountable controller, which is a 160 watt controller that contains all the VFD stuff and all the driver transistors and well, basically it does all the things and also has some brain power and can actually monitor the status of the pump and shut it down if it gets too hot and stuff like that. It's pretty simple to interface. It just needs some voltage and then basically just needs a button to turn on and off the pump, and that's it. It also has an analog output of motor speed, so you can display or monitor the pump speed. A pump that's running nicely should run around 80 to 100% speed. So that's like a really useful little module. Unfortunately, this one needs an 80 volt DC power supply, which is going to be a challenge. Either way, I have a vacuum gauge here. It's a little active Pirani gauge, also Edwards. They came from the same lot. It's a mass spectrometer that was torn down. As with the pump, it's pretty easy to interface. It just has like an RJ45 kind of plug. You basically just give it 24 volts and then it gives you an analog reading out. I've just put a panel meter here and I have a switch so I can switch it on. And it shows full pressure, which it should. I haven't tried this out at vacuum since I don't really have a pump yet. And that I just calibrated this scale with the values there was in a list in the manual with a voltmeter and a power supply. It also has a nice feature. It has a set point that you can set with like a little potentiometer, and you can display the set point on the meter. And this set point, going above or below it activates a 24 volt digital output. So you can monitor or set fault or safety interlock systems for things that absolutely do not stand to be turned on while there's pressure in the system. Now this goes down to something like 10 to the minus fourth millibar, which really isn't enough to go down to turbo pump pressures, but it's a good rough indicator. These are often used on the low pressure side on the turbo pump to monitor the backing pump, but I'm going to use it side by side with a Penning gauge or a cold cathode gauge or whatever I can find. But yeah, it's quite nice. It looks to be working. Right now I have no real power supplies. I can show you the electronics. It's not pretty. It's not that bad, but it's not. I mean, it's some switches and everything is happening in the controller. Right now I'm just using this in lieu of a 24 volt power supply. As you can see here, the circuit isn't that difficult. You have these pins here, so you give it 24 volts, you give it a meter, and you can use the set point if you want. It just has the switch here and it has the set point out here. And the power supply for this entire system will be situated somewhere in the back here. Now try and get a 72 to or 80 volt switch mode power supply. It's not easy. It's at least not if you're cheap as I am. So I'm going to serialize a 48 volt and a 24 volt supply and also use that 24 volt as a tap out for all of the low voltage stuff and the relays and the meters. That shouldn't draw more than 100 milliamps max, so I think that's fine. I'm going to over-dimension the power supplies by about an amp to be certain. The pump is going to draw something like 2 amps at 80 volts. Now the pump control is equally simple. I haven't built this yet. It just has a push on, push off button. It has a pump normal lamp that turns on when the pump is at over 80% speed, I think. And it has an analog speed output meter. And then it has the power input. Now one more thing I want to add to this system. I've made provisions that I have room for a lot of auxiliary stuff and relays and stuff to control other things, but that's why I've made this so sturdy. This is not a cabinet. This is just a 3-4 millimeter front plate and a bottom plate that's thick with some angle irons here. This is just so I can bolt stuff to it without taking other stuff off of it. I want a solenoid valve to bleed out the vacuum. Now, the way you break the vacuum on these pumps, the way you turn them off is you wait until you've turned off this pump. You've waited until the vacuum is down to around 40% speed. That's why you need the speed gauge. Then you slowly crack this valve. This is just like a needle valve or like a low flow valve, and then you suck some air into the pump. And that helps, of course, helps slow down the pump faster, and also helps break the vacuum for the oil pump. Now, you never ever want to turn off the rotary vane oil filter pump before you've broken the vacuum, because if there's still enough vacuum in the system, it'll suck back the oil into your turbo pump and into your system. Now, the manual for this actually says that you should put a valve in between the backing pump and this pump. I've never seen that done in practice, though. I think on smaller vacuum systems, like on mass spectrometers, I've seen this exact pump with just like a flexible hose to the forward pump, and then you basically just turn this on at the same time as the backing pump, and you close whatever valve you have. And they basically spin up at the same time, and the turbo pump survives that. It's not that fragile, but you should still be careful with it. And especially if you have a large volume or large chamber that takes a long time to pump down, then you'll need to have switching so you can pump it down with the forward pump first, and then switch to this one, and then have them running in series. Now, what I want to do is replace this with a solenoid valve, and then add the controls for that to the front panel. And the philosophy for that basically is that I want everything to be remotely controlled from this panel, so I don't have to go near the vacuum system while it's running. It probably won't be an issue. I'm not planning to do anything inherently unsafe with this, but having ultra high vacuum, having high voltage, having potentially either hot surfaces, you usually with these vacuum systems, you bake them out, you wrap them in something heating and heat them up to 120 degrees C while they're running to bake off anything that's volatile. Or something cryogenic if I want to have some kind of trap. And also, every time you have high voltage and high vacuum, you have the potential to create X-rays. So basically, being able to have this entire setup, like everything connected to the pump, the entire vacuum system, on a little trolley that you can move away from you, is just a nice peace of mind thing. Now, ideally for this setup, I would have a large-ish vacuum chamber on top of this with a lot of ports and maybe a sapphire viewport and a residual gas analyzer, but that is tremendously expensive. I think phase 1 vacuum chamber is going to be a large KF50 50mm internal diameter with kind of these flanges cross or a 6-way fitting. That'll give me a lot of ports and pretty large volume to do stuff in. I'm going to mount all my experimental setups on like narrow aluminum sleds that'll just slide into the vacuum tube, and everything will be solidly located within the experimental setup, and then I can make whatever I want of feed-throughs. So that is the status of my high vacuum system at this point. I'm hoping to update this pretty soon, but I still don't have a vacuum pump, so it'll probably take a while before I can actually run this. I hope you found that interesting. See you next time.